prove by contradiction that there are no positive integer solutions p and q such that 4p squared minus q squared is 25. So, for proof by contradiction questions, the first thing that we get is our assumption. And our assumption in this case would be, well, first of all, it's the negation of the statement that we have here. And the negation of the statement is that there is at least one set of positive integers p and q such that 4p squared minus q squared is 25. And then with that, 4p squared minus q squared is 25, notice how this is, on the left-hand side, the difference of two squares. So that means we can factorize using the difference of two squares. This becomes 2p minus q, 2p plus q. Just bear in mind that difference of squares often helps you solve proof questions, so always keep that in mind, that you can convert what we have here into something like this. So we know that p and q are integers, so if p and q are integers, that means that 2p minus q and 2p plus q would also be integers. So we have an integer times an integer is equal to 25. There's only a few ways in which we can achieve that. We can have 2p minus q being 1, 2p plus q being 25, or them both being 5, or this being 25, and this being 1. And then we can solve those sets of equations simultaneously. So we can solve 2p minus q is equal to 1, and 2p plus q is equal to 25. Do the same thing for these two and these two as well. So I'll just write them down. And when we solve these three pairs of simultaneous equations, we won't find integer sets of solutions for p and q. So let's start with the first one, on the left-hand side. If we add the two equations up, we end up with 4p is equal to 26. And then we end up with p is equal to 6.5, and that's not an integer, so we can stop there. This doesn't give us an integer set of solutions. We get the same thing with this pair of equations here. So if we added the two things, we'd get the 4p is 26 and then p is equal to 6.5. But actually, what we have here wouldn't give us, or wouldn't work anyway, because we're told in the question that p and q are both positive integers. So then 2p minus q wouldn't be bigger than 2p plus q if p and q are positive numbers. So we can rule that out straight away because of that. But rather than having to write out what I just said, we could also just do this. So for the middle one, add them up, we get 4p is equal to 10, and that gives us p is equal to 2.5. For these three sets of simultaneous equations, we don't get an integer solution for p. Therefore, we won't have a pair of integers p and q such that this is true. And there's our contradiction. So p is not an integer, which contradicts our assumption. And then we just have a brief conclusion which repeats the question back. So we have therefore proved by contradiction that, and then we just rewrite the question for our conclusion.